Okay, let's proceed to number 2. F of x is x to the n, where n is a positive integer. So again, the same task, we will be solving for f prime of x. So we will use the definition of derivative, which is f prime of x is equal to the limit of x plus h to the power of f. No? F of x plus h minus f of x all over h as x approaches to 0. So again, we will be using the same definition of derivative for solving all these problems here whenever you are asked for the derivative. So, solution. Okay, very similar. We need to find f of x plus h, because in our formula, we need to find f of x plus h. So, our function is defined to be f of x, x to the n. So whatever is this value inside here, it is the one raised to certain n. Okay, so we have here x plus h to the n. So, how will you expand x plus h to the n? So, how will you expand that one? So suppose you have x plus h squared. That is simple, where in this case n is 2. So you have x squared plus 2xh plus h squared, right? So x squared plus 2xh plus h squared. Simple. For instance, you have x plus h cubed. You can expand it. You have x cubed plus 3x squared x plus 3x h squared plus x cubed. The bigger the value of your exponent, the more terms you will have on the right. So, much to it if you have, for example, x plus h to the 100, right? So, it's already a very long expansion. Much more with n, because n here could be 1,000. Your n could be 1 million. As long as it is an integer. So, how will we expand this one? So, there should have a procedure, right, of how we are supposed to expand x plus x to the n. Okay. So, of course, if you could recall your Pascal's triangle, that's helpful, right? So how do you make Pascal's triangle? It's just 1, 1, 1, 2, 1, 1, 3, 3, 1. This is for the expansion of x plus h to the 0. This is the expansion of x plus h to the 1. That is the expansion of x plus h to the 2. This is the expansion of x plus h to the 3. That is why, that is why you have here 1. There is a 1 here. There is a 1 here. So this is 1, 2, 1. 1, 2, 1. There is a 1 here. 3, 3. There's also 1. So it's 1, 3, 3, 1. 1, 3, 3, 1. Okay? So, if you have x plus h to the 4th, you just have to add this one. So, you have here 1, 4, 6, 4, 1. So, you have 1x cubed, 1x to the 4th, plus 4x cubed, h, plus 6x squared, h squared. The trend is the exponents of x are decreasing. 4, 3, 2. The exponents of x to the 0 is 1, x to the 0, x to the 1, x squared. Plus 4, x to the 1, okay, x to the 1, h cubed plus 1, 1. X to the 0, that is 1, h to the 4th. Okay, so more or less like that. So we can predict, no? So what is important here is this. There's always one on the leftmost part, and there's always also one on the rightmost part. No? And you see that the Pascal's triangle is somewhat symmetric along something here, because here you have 4 and 1, 4 and 1. No? So if you can continue this, so you have 1, 5, and so on. If you continue here, you have 1 and 6, right? So if you look at the number, it's like this. No? So we would expect that for x plus h to the n, there is always a 1 here. So 1, x to the n, no? H to the 0, right? X to the 0, or that is just 1, plus, what happened to the next term? If it is 3, no? This 3 is 3 here. X plus h to the 4 is always 4. 4, so there's always 4 here. No? Plus, if you have, for example, 5, so to the 5th, so there is always 5 here. So what do you expect when you have an n here? So it's like n, you have x, n minus 1, h, right? So, okay, so let me just make this one clear. No? So you have 1, 4, and 1. So 5. 1, 5, 10, 10, 5, 1. This is for x plus y to the 5th. And then what will be the next row? 1, 6. So that is x plus y to the 6th. So continue. 15. Okay, there's a number there. And then for x plus y to the 7, 1 and 7. So in the expansion, 1 followed by 7, right? So therefore, for x plus y to the n, there's always 1. What will be the next here is n, x to the n minus 1. You have y to the 1. Okay. So x to the 1 plus. Now, I will just denote the rest of the constants here. Instead of writing like this, I can just write them. Anyways, there is a reason why I'm doing this one. I can just write first, second, third. I have here c sub 3 x to the n minus 2 h squared. I just write it this way. I am just so particular with the first and the second term. The rest I can just, for example, this one, no? 1, 4. I just write it as c sub 3. 1, 5, c sub 3. 1, 6, c sub 3. 1, n, this one. And c sub 3, the rest. Plus, you have c sub 4, x, n minus 3, h cubed. So the exponents of x are decreasing. N minus 1, n minus 2, n minus 3. The exponents of h to the 0, h to the 1, h squared, h cubed, plus that. The last term here, the last 3 terms, we would expect it to be, okay, let's analyze. So, it's like, you'll be, again, going back to 4. What is this value here? Because we said it's symmetric. So there is a 4 here, 4 here. So we would expect that the last part here is somewhat n, x, and you have here h, n minus 1. You look at here. 4, okay? No? Okay, h, n minus 1. And finally, plus the last part, which is actually 1, h to the n. Okay. So again, I am just so particular with the first 2 terms and the last 2 terms. Why is that so? Because based on the Pascal's triangle, it's like symmetric. 1, 4, 4, 1. 1, 5, 5, 1. So I just write those other terms in between as C sub 3, C sub 4, and so on. Okay? So that is how we expand f of x plus h to the n. Now, let me erase this part. So, I'm applying now the formula. F prime of x is equal to limit of, I'm sorry, long really. F of x plus h, this is the value. So I have here, I won't be writing any more 1, that's x to the n plus n, x to the n minus 1, h plus c sub 3, x n minus 2, x squared plus c sub 4, x to the n minus 3, x cubed plus, there are still c sub 5, c sub 6, c sub 7 plus that, and the last two terms, let's write it this way, n, x, you have h to the n minus 1 plus h to the n, no? Minus, because the formula here is minus f of x. And what is our f of x? X to the n. So I'll write here x to the n. All over h. As h approaches to 0. Okay. Now, of course, this one will be 0. So you'll be left with limit of n, x, n minus 1, h plus c sub 3, x to the n minus 2, x squared plus c sub 4, x to the n minus 3, x cubed plus, you'll be left with n, x, h to the n minus 1 plus h to the n all over h as h approaches 0. Now, look at this. H's are common for each term. This is h, this is h squared, h cubed, h to the 4th, and so on, h to the n minus 1 until h to the n. So therefore, we can factor out h, right? So we factor out h, so this is limit of, I'll factor out h. So I'll be left with, in this case, you have n, x to the n minus 1, h, okay? We factor this out, so we have here c3, x to the n minus 2, h to the 1, okay? Because 1h is placed here or factored out, plus c sub 4, x to the n minus 3, h squared, okay? Plus, plus, we take 1h here, so that becomes h to the n minus 2, okay? Plus h to the n minus 1 all over h as h approaches 0. So this is just 1. So you'll be left with limit of n, x, n minus 1 plus c3, x, n minus 2, h plus c4, x, n minus 3, x squared plus you have h, n minus 2 plus h, n minus 1 as h approaches to 0. Now, when we evaluate this one, so we apply the limit theorems we have before, what will happen? This term will be constant. Tapos we substitute here 0. So we have here, what will happen is you have n x to the n minus 1 plus c sub 3 x to the n minus 2 times 0 plus c sub 4 x n minus 3 0 squared plus that is 0 to the power of n minus 2 plus 0 to the n minus 1. So this expression multiplied with 0, that is 0. 0 squared, that's 0 times this, so it will become 0. 0 to the power of a positive integer, because n is a positive integer, so this is 0 and this is 0. So what is left? The term left is only n x minus 1. So this is our f prime. So, what should be the answer for our problem? F of x is to the n, where n is a positive integer. F prime of x is just equal to n x n minus 1. So, this is the derivative.